Hello, it's Keith here, and this is lesson 12 of the YQuest series of 6502 assembly programming tutorials. Now we're back on the NES again today. Why are we looking at the NES again? We've seen it before. Well, this time we're looking at sprites. We've added hardware sprite support to the NES game, and that means that we now have some nice smooth movement. Look at that. And we also have more colors. Because we were defining the entire tilemap to be the same colors because of the difficult limitation of colors being defined at the 16 by 16 block level on the NES, we were unable to make very good colors. Now the background, the text is still being done by the tilemap. Now we're using hardware sprites for all of the game objects. We can have a bit more color in there, so that's another big benefit. So today we're going to look at the changes that were made to YQuest to support hardware sprites on the NES. So let's go over to the code and let's have a peek. Okay, so here is the NES version, NES YQuest12, and first we're going to have to discuss the changes that were made to the common code. Now the first thing is the unused byte of the object definitions is now a hardware sprite number. If that's a 0 or 255, the object isn't using a hardware sprite. I use 255 as being disabled because the bullet array is reset to 255. Anything else is a hardware sprite, and that's the number of the hardware sprite. Now on the NES that's going to be 0 to 63, otherwise you're going to have a bad time. So we're going to use those hardware sprite numbers. And also as well in the RAM definitions, the player object is now using hardware sprite 1. We're defining player H sprite as 1 at the top of our code just here. So that's defining the player as using a hardware sprite. Now the multi-platform code has had a few changes. The end of the drawing routine here, the moving and drawing routine, is now checking the H sprite number of the object. If that's between 1 and 128, it's assumed to be hardware sprite 0 to 127. Otherwise, it's being drawn with the old Tilemap code. In addition to that, we need to set up all of the objects with hardware sprite numbers. So we have a quick function to do that just here. This will set consecutive objects within an object array with consecutive hardware sprite numbers, and that's going to be needed. Now, on the NES, hardware sprites are kind of simple and they're kind of tricky because we just have 4 bytes that define the position, then the tile number of the hardware sprite, and also we can X flip and Y flip, and we can put them in front of or behind the background. We also have the option for 4 possible pallets. However, they're a little bit tricky because just like with the tilemap, we can't write them except outside of except in VBlank, so when the screen's not drawing. The good thing though is that unlike the tilemap, we can actually use something known as a DMA, which directly transfers all the data for us. It's specifically designed for this kind of thing, so that's going to make things a little bit easier for us. So what we're actually going to do is we're going to define a sprite buffer. We define it just here, and this has got to be 256 byte aligned, just because that's the way the DMA works. And what we're doing here, we're just zeroing that buffer, resetting all the data. We do that in clear screen as well. And then when it comes to our interrupt handler, we just have 2 lines here to actually support the hardware sprites. So this interrupt handler works during VBlank. If you don't know how that works, please see the original YQuest NES tutorial where we looked at how to use VBlank to set up a tilemap, or copying the tilemap in VBlank. So in this case, we just take the top byte of the sprite buffer. That's why it's got to be 256 byte aligned, and we're dividing by 256 to get that top byte. We store that to 4014, and that will start the DMA transfer to OEM, which is hardware sprite RAM. And that actually does all of the hardware sprite work for us. So now we can actually just store to the sprite buffer in normal memory, and that will actually basically get the sprites working for us. Everything else is being done by that interrupt handler. Now, we're defining our pallets the same way as before, but there's now more of them. We've now defining 8 pallets. These work in backwards order, so this is the first 4. These are the tilemap pallets, although we're actually only using the first one. But we now have 4 sprite pallets as well, and we're defining those in different colors. And we've actually defined some pallets for our hardware sprites. Our hardware sprites actually use the same bitmap data as the tilemap, but we're also defining a pallet, and you can see it's just a single byte that we're going to transfer into the hardware sprite data. Okay, so that's what we're doing there. Now at the start here, we are clearing the sprite buffer here. We're turning on some extra memory. We've got some memory in the cartridge, so to speak, the virtual cartridge, and we're using that because we're using quite a lot of memory now with all of this. And basically, we then have to turn on the sprites with this command here. We've changed this code here so that we're now turning on hardware sprites. Otherwise, we won't be able to see anything, and that would be rather disappointing. Now, at the start of our game code, we're allocating a hardware sprite number to each of the objects and setting that 1 byte of the object definitions to a hardware sprite number. So hardware sprite 2 in that definition will be really hardware sprite 1, because we subtract 1 from each one. That's so that 0 is unused, whereas actually 0 is the first hardware sprite. So we're adding these numbers to each of these hardware sprites. So we're adding a hardware sprite number to each of these objects, and that defines them as being drawn with hardware sprites. Now we've got the do blank code here, and this is now checking the hardware sprite number, and if the hardware sprite is to be blanked, then we're actually moving the hardware sprite off screen, and that will basically make it invisible. That's a quick way of blanking the hardware sprite. When we want to actually draw our sprite, we've got this new doGetH Sprite Object. This is a modified version of doGet Sprite Object. If you remember, this gets all of the settings from the object definition, and it's doing the same now. It's just been changed to use the hardware sprite. So we're selecting the pattern again. It's the same pattern data as before. We're now loading in a byte from the sprite pallets defined by the object sprite number, the software sprite number, that is, the tile number, I guess. And so that's being loaded in and stored in L. We're calculating the X and Y position here. This time we're working in pixels, not 8x8 blocks, so much nicer movement there. Actually, the internal logic of the X coordinates only works in pairs of pixels, so it's actually now too low resolution. So we're shifting the X resolution to the left once there to effectively double it up there, because, as I say, the resolution of the internal calculations was designed for a potentially 320 pixel wide screen, just storing the X position in a single byte. Now the offset, we're adding 16 to the Y position, because 0, 0 is actually off screen, so we're just doing that to get our hardware sprite to appear at the same position as the tilemap, so the two line up. In theory we could do half the objects with the tilemap if we needed to, but the NES has a lot of hardware sprites, so we don't need to. And here's the code that transfers the data into the buffer, because remember we can't write to direct to VRAM. So we're just transferring the Y position, the tile number, the attributes in this case, which is just the pallets here, and the X position here. Those are all being transferred into the buffer there, and actually all of the work is being done by that NMI, as I said before. Here, it's that's actually transferring them to the hardware sprites, and as long as we've got those set up, it will draw them to the screen, and that's really all it takes. So it's not actually too bad. Getting the tilemap working was a bit of a nightmare on the NES, because you actually had speed limitations. You couldn't get all the data transferred in VBlank, and you had memory limitations because you needed so much memory for this massive tilemap. Whereas the hardware sprite is just 256 bytes, and you've got this nice DMA command to do the work for you. So very good there. So that's all it takes to get hardware sprites working on the NES. Now, of course, you can make tile and sprite graphics with my Sprite editor, the free open source editor, which I use, and it's included in the downloads for this lesson and all my lessons. So if that's any use to you, go ahead and grab that. As always, you can download the source code for today's episode, the build scripts and the emulators and things, and hopefully you can compile this yourself and have a go with it. And as I always say, you're welcome to use any of my code in any way you want, even commercially, and I don't care if you give me credit or not, because it's supposed to help people. So give it a go. If you've liked this video, please like and subscribe. If you like the videos, YouTube recommends them to more people. People apparently don't know that, but that's the way they work. So that's a help. And if you subscribe to the videos, it just generally encourages me to keep making them, because I keep making all of these endless tutorials, and it takes a lot of time. So if you want me to keep doing that, if you'd subscribe, it would help out. Anyway, whatever you decide to do, I wish you all the best with your NES programming. I hope you have a lot of fun with it and a lot of success. Thanks for watching today, and goodbye.